My name is Bernardo, and I'll explain about my thesis. My thesis is the pattern set representations using linear, shallow, and tensor subspaces. I was advised by Professor Orlando and Professor Valdir. So this is our agenda. I'll give some motivation and background on subspace analysis, and also introduce our work, which is the new representations, shallow networks, and tensor subspace. I will also give some hints for future directions. So most of the problems that we solve with machine learning and computer vision, they rely on the fact that we just have one observation of our objects, or of the objects that we are studying. For example, usually we just classify one image or one video of the object that we are analyzing. But most of the time we have many frames, many pictures, many observations of the same object, which give us the idea that we can not only classify patterns, but also set of them or bags of them. So one of the advantages is that sometimes it's difficult to classify some objects when we just have one image. However, when we have many observations, for example, we can avoid problems such as occlusions or illumination conditions. So some algorithms, for example, PCAs, SVMs, and neural networks, they can just work with one pattern at a time. In our work, we will show that we can work with many patterns at once. So these are some warm-up examples. So most of the time for gesture recognition, action, and even face recognition, we have many images of the same object that we are analyzing. For example, for gestures, we can have many frames of the same gesture, and then we can work with all them, which can give us more reliable algorithms. Now I will explain what are and why do we use subspaces. Subspaces are just an algebraic object that are formed by basis vectors. These vectors, they have unit length, and also they are orthogonal to each other, which give us many advantages. For example, we don't have a redundancy, and also they can compactly describe many kinds of data. So this is one example. So most of the time, we understand that the data, it often resides on a subspace. And also in this example on the left figure, we can see that many points, they are clustered, and they can sometimes be represented by a plane instead of being represented by these points. And also, if we work on the feature space, it is difficult sometimes for the algorithms to obtain a reliable number of points for learning. However, if we project them on a subspace, the number of dimensions will reduce, and then we will be able to learn the algorithms. So this is one of the frameworks that we use. This is the mutual subspace method. Mutual subspace method creates the subspace using the eigenvalue decomposition. The eigenvalue decomposition gives a set of base vectors. And then these base vectors, they have a special attribute where the vectors, they are ranked regarding their importance, more precisely the variance. And then this ranking can give us hints which of them are more important for classification or for representation. In our case, we can select the most important ones based on eigenvalues, and then discard the less important one. So the subspace can be very compact and represent much more amount of data. So this is our first contribution. So we employed the two-dimensional PCA, which give us some advantage over the one-dimensional one. It also makes the subspace very compact, and also we can make very fast algorithms. We also understood that the ordering of the patterns is not preserved when we use the one-dimensional PCA. And then we also introduced the Hankel subspace method. So as we can see, if we change the ordering of the patterns, ordering of the frames, we can get always the same subspace. So in this particular scenario, we are not able to represent, for example, gestures or actions that are determined by the ordering of the frames. So by using the Hanko subspace, we concatenate the images in a way that when we apply the eigenvalue decomposition, we can create a time signature of them. And because of this time signature, we can classify gestures, for example, or actions. So this is our understanding. So by shuffling or changing the ordering of the frames, we can create a signature and then classify them. This is our framework. So by making the eigenvalue decomposition on the Hankel matrix, we can create subspace that can preserve time information, and then we can classify a classification of the subspace. We can use the canonical angles to understand the distance between them and use the nearest neighbor classifier, for example. So now I introduce shallow networks. We understand the shallow networks are networks that they have very few number of layers. However, they have one advantage, which is that they don't rely on backpropagation. So they are very fast, and we can use low computational resources to train them. Our solution is based on subspace, and then we use a subspace not only to represent data, but also to extract discriminative information. We use the same framework. It's based on eigenvalue decomposition. However, we introduce a novelty, which is the Fukunaga-Kuntz transformation, which orthogonalizes the subspace. So it gives, for example, gives some weights to the subspace, so it can decorrelate them. In this decorrelation process, we can extract more reliable information for classification. So this is an example of how we create filters. These filters can be employed as convolutional kernels in the convolutional neural networks directly, so we don't need the backpropagation. And then we can use many layers and also pooling layers and so on. Now I'll explain a little bit about tensor analysis. So tensors, they can be seen as generalization of a matrix. And because of tensors, many applications we can solve using tensor representation. So for dealing with the tensors, we should understand how to unfold them correctly. So many types of unfolding procedures are available. The unfolded representation facilitates the use of the subspaces. So we can use the subspace on each one of the unfolded sets, and with these subspaces, we can compute the geodesic distance on a manifold. So if we understand the subspace, the collection of subspace, we can understand that this collection can form one manifold. This manifold can be used for calculating the geodesic distance, which we use it for computing the similarity between the subspaces. So this is our framework. Our framework, we for this example, we use a three-mode subspace, three-mode tensors. However, we could use many dimensions, many modes. So we project our subspaces on discriminative space created by Fukunaga-Kuntz, and many others can be used as well. And then we can use the product of the manifolds to compute the geodesic distance. Some remarks. So this method can be used for tensor representation, and we can use them not only for classification, but also for some supervised learning and many others. We simplified the process of representing tensors by a set of linear subspaces. And also we have some advantages such as low memory requirements. The tensor matching is facilitated by the geodesic distance. And we can also extract discriminative information. So for future directions, we will investigate how to express other kinds of data with subspaces. We can also create other kinds of shallow networks using other manifolds. We can use a kind of initialization based on the weights that we created from the subspace, and then we can represent and classify multimodal data. So these are a list of our main publications that we published regarding our shallow networks, dense subspace, and our new representations. So thank you very much for your attention.